Hi, everyone. Thanks for joining us today. We're excited to present you with some information on the impact of the cryo-cooling process that can have on the quality of diffraction data. We'll begin shortly, but first, I just want to provide a little general information on the webinar and the best ways to interact with us. So I'm Ben Apker. I'm the Chief Operating Officer here at Mitogen. I'll be serving as the facilitator today. If any of you have challenges with observing the webinar, I'll do my best to be able to help you get back online and assist you. Please note that we are recording the presentation and we plan to make it available to all the attendees shortly after the conclusion. We hope that what we present will be informative and we want to engage with as many of you as possible. So we've enabled the Ask a Question feature on your displays in the lower right. Please freely chat questions or comments to us. They'll come directly to me and we hope to address as many of these as possible after the presentation. It looks like we have quite a few people in attendance today, so should we not have time to answer all of your questions live, we'll be certain to follow up with each of you directly and get the information you've requested. Note that the general chat and microphones for the attendees have been disabled. Also, there are a couple of PDF handouts available to you in the handout section. We encourage you to download those and have a look. The goal is for us to provide you with some information on the impact of cryocooling, how some of the technology we've developed stands to improve the data collection outcomes, and how you can get access to that technology. So please allow me to hand off and introduce Mitogen's founder and Chief Technical Officer, Robert Thorne, who will be doing the presentation from here.
All right, so welcome everyone. Today I'm going to tell you about Mitogen's advanced cryocooling technology and how it can transform your cryocrystallographic practice. We need great crystals to get great data and great structures. And we also need to make sure that those crystals stay great all the way to the end of data collection. Getting those crystals requires a lot of time and resources. And so once you have them, you want to make the most efficient use of them. You don't want to damage them or waste them. So you want to use protocols that will maximize your data quality, maximize your throughput, minimize crystal-to-crystal variability, and minimize the risk of crystal contamination, damage, and loss. It's with all of these ideas or goals in mind that we have developed our Nanuq automated cryocooler. There are many challenges in biomolecular cryocrystallography. First, cooling always damages crystals, sometimes a lot more than others. And especially, damage is severe if internal ice forms. Ice can form both inside and outside crystals, and the diffraction pattern shown here is an example when ice is formed inside the crystal, creating these uniform ice rings and causing a severe loss of ordered diffraction from the protein structure. Ice can also accumulate in the liquid nitrogen that we use to cool the crystals and contaminate their surface and the diffraction patterns. A recent analysis by Andrea Thorne and others showed that 20% of PDB deposited data sets show structure factor errors due to ice, and that's the PDB data sets are our best data, so presumably ice contamination is a much larger problem than that. Ice formation is a particular problem with some of the highest value targets, such as membrane protein crystals that have large solvent contents, and crystals of large complexes which have large solvent cavities. So ice is a problem. If you have ice, you can reduce or eliminate it by adding enough cryoprotectant, and that's shown in the figure here, where we have drops of water plus cryoprotectant. I think in this case it was PEG. And as we increase the concentration, so these are frozen drops, and as we increase the concentration of PEG, eventually we reach a concentration where the drops are clear, indicating that they're vitrified. So that in principle works. The problem is that cryoprotectant soaks can damage crystals. They can crack them or change the protein conformation. They can also dissolve the crystals when the cryoprotectant concentration is large. Something that's not as widely appreciated is that cryoprotectants reduce the or increase the electron density of the solvent, and therefore reduce the electron density contrast between the protein structure and the solvent, and reduce your achievable resolution by a couple tenths of an angstrom or so. Cryoprotectants also complicate the electron density in your solvent cavities, and they can displace weakly bound ligands or else be mistaken for ligands. And this is a particular problem if you're, for example, doing something like high throughput fragment screening. So most cryocooling is currently performed by plunging crystals by hand into liquid nitrogen. The amount of damage caused by cooling depends on the cooling rate and the cryoprotectant concentration. Cooling rates in hand plunging are typically in the range of 100 to 1,000 Kelvin per second. So you do need cryoprotectants to eliminate ice, especially in the solvent surrounding the crystal. The cooling times in hand plunging are between 1/10 of a second and a second, which is too long to kinetically capture the biological temperature structural ensemble. And the work of James Fraser and others has shown just how much information can be lost as a result of cryocooling using conventional methods. Another major challenge is that cooling rates in hand plunging are highly irreproducible. Above the liquid nitrogen in your dewars is a layer of cold nitrogen gas, and for protein crystal size samples, a lot of the cooling occurs in that cold gas layer. And since the thickness of that layer depends on how full the dewar is, whether the air conditioning's on, whether someone's walked by your crystal mounting station, there's a lot of variability in how much cooling occurs in that gas layer. And then there's also variability because of variability in the speed with which you manually plunge the samples through the gas layer and into the liquid nitrogen. So all of this gives as much as a factor of 100 variability in cooling rate in manual plunge cooling. And that is a major cause of crystal non-isomorphism. Another problem is if you find that one crystal diffracts better than the next, you don't really know why that is. Was it because of how it grew, how it was cooled, or something else? An additional problem in manual plunge cooling is that the crystals are often lost either during the plunging process, maybe because you bang the loop in the bottom of the dewar, or during loading of the frozen sample into a cryovial or into a puck when you bang the side of the puck. And so loops sent to synchrotrons often arrive with no crystals in them. What would an optimal cryocrystallography workflow look like? Well, first thing you want to do, which unfortunately very few people do, but they should, is to mount their as-grown crystals and check their diffraction at room temperature using Mitogen's micro-RT system. Cooling almost never leads to improved crystal order except for reduced thermal disorder. It almost always increases crystal disorder, so get rid of the bad crystals from the start. And also start with good crystals so you have some idea whether your cooling process is problematic or not. Next, to maximize isomorphism, you want to harvest your crystals in a humidity-controlled environment and keep them from drying out. And I'll just make a plug for Mitogen's watershed humidity control system. This system allows you to program any humidity that you want, and it has two end stations, a nozzle, and an end station like this that takes glass cover slips that provide humidified environments for harvesting and soaking and manipulating your crystals. You can also use the nozzle here or this station to programmably dehydrate your crystals, which can sometimes improve their diffraction. So then in harvesting, ideally you don't want to have to use any penetrating cryoprotectants. You just want to do a quick swipe through oil or a 10% cryo solution just to minimize or prevent ice formation in the external solvent around the crystal. And then you want to remove as much of that excess liquid as possible from around the crystal. Next, you want to cool as fast as possible in liquid nitrogen that has no ice in it, and then store the crystals in an ice-free environment until data collection. So that's what we'd like to have happen. And so Nanuq allows you to achieve many of those goals. It eliminates ice formation and ice contamination. It minimizes sample-to-sample variability. It gives you complete control of every plunge. You can do ultra-fast cooling, slow cooling, or anything in between. If you're in a big lab with a lot of different people freezing samples, Nanuq allows you to standardize cooling for every crystal and every user. And it automates critical steps between crystal harvesting and X-ray data collection that are a frequent cause of lost crystals and data. The basic design of Nanuq has three key, or addresses three key challenges. The first is the management of cold gas and the plunge environment as the sample is translated into liquid nitrogen. The second is the speed with which the sample is plunged into the liquid nitrogen. And the final is how the samples are stored after they've been cooled. So if you want to cool as fast as possible, we call this hyperquenching. This is what a plunge sequence will look like. Here's a sample on a wand. Here is a unipuck. Here is liquid nitrogen. And here is the cold gas that is formed above the liquid nitrogen. And this area here is we call this the plunge bore. When a plunge sequence is initiated, the first thing that happens is that the cold gas above the liquid nitrogen is sucked out and warm gas is flowed in to replace it, so that there's an abrupt transition between warm, dry gas and cold liquid nitrogen. Then the sample is plunged at 2 to 3 meters per second into the liquid nitrogen. And then finally, it's slowly translated into the unipuck, and then the unipuck rotates to the next position to accept the next sample. So fast cooling is a really good thing. In most cases, it's what you want to do, but it may not always give the best results. For example, if you have very large crystals, hundreds of microns in size, if you try to cool them really fast, they can develop large internal temperature gradients, and that can lead to fracturing and damage. A second thing is that as the crystal cools, the protein structure is contracting, but the solvent inside the crystal may contract or expand, and there's a redistribution of solvent that occurs inside the crystal during cooling. And if you don't give enough time for that redistribution, it can increase your mosaic disorder. So if you have a crystal with a huge unit cell and you're really worried about spot overlap and want to minimize that spot overlap and minimize mosaicity, it may be that cooling much more slowly will give you lower mosaicities and reduce that disorder. Another thing that can happen is that sometimes for some proteins, the protein and or the lattice may undergo favorable relaxations during slow cooling that improve overall crystal order. It's similar to what happens in dehydration. There can be repackings that occur that improve order. So Nanuq is designed not only to give you ultra-fast cooling, but also to give you a slow and variable rate cooling. And so in the slower variable rate cooling plunge sequence, here's your sample, the cold gas layer, and the liquid nitrogen and your puck. In this case, we leave the cold gas layer in place. We let it build up, and then we slowly plunge the sample through that cold gas layer. And the cooling rate in this case will be determined by how long it takes the sample to go through from the warm air up here to the liquid nitrogen down here. So it's controlled by the plunge speed. And then once you're in the liquid nitrogen, the sample is again translated into the puck, and the puck rotates to the next position. So a little bit about the hardware that we've designed and patented to do all this stuff. A major part of our design effort was in the design of this plunge manifold, which sits on top of the liquid nitrogen dewar. And it's what sucks away cold gas, delivers warm gas, and more important, it isolates all of the cold surfaces down here from the warm, moist air up here, and has heaters and other features that eliminate frosting and prevent contamination of the liquid nitrogen down here with ice crystals. So it controls the plunge environment to either remove or define cold gas layers above the liquid nitrogen. It eliminates cold gas if you want the fastest cooling. It traps it for slower variable rate cooling. It also eliminates waves on the liquid nitrogen surface that can happen when it's boiling, which helps give you the fastest cooling. It isolates the cold surfaces from the warm ambient air. And everything is under computer control, so you don't have to worry about it. And it also helps, the controls are optimized to minimize liquid nitrogen consumption. The next important piece of hardware is our sample translation stage, which, unlike in cryo-EM plungers, which only plunge at one high speed, this one can do arbitrary motions at speeds ranging from 3 meters per second down to less than a centimeter per second. And so you can plunge fast for the fastest cooling or plunge at other speeds for slower cooling. Nanuq holds up to 4 unipucks and 64 samples in liquid nitrogen, and we designed this quite sophisticated system that operates in liquid nitrogen for positioning the samples. So you can program samples after they've been cooled to be loaded into the pucks in any sequence you want. So you can fill the pucks in a way that will organize your samples for optimal synchrotron data collection. Loading the pucks into and out of Nanuq, and taking them out afterwards is easy. And the key thing is that all manual handling of cold samples is eliminated. So you're not going to bang the samples into the puck or have other accidents like that. And then it is designed with a large liquid nitrogen storage capacity to allow at least 12 hours of continuous operation without frosting. Then as I already said, the operation is all computer controlled, and I can show you a video here of gives you an idea how the plunging works. So there's Ben, he's harvesting a crystal, and on a wand he pops it in the machine, he closes the door. As soon as the door closes, it plunges the sample. The first thing, if we had the sound up, you'd hear when the door closes is you'll hear a whoosh of gas. That's the cold gas layer being removed and the warm gas replacing it. And then the samples plunge. So you can see it's a very fast process. There's no real opportunity for samples to dry out. And it's about, from harvest to plunge, it's less than 4 seconds. And you can do a few samples per minute. This shows what the computer interface looks like. It's pretty straightforward, gives you complete control of everything you want to have control of in a straightforward way. So what about performance specs? So this is some data for cooling rates in nitrogen gas streams and in hand plunging. These are taken from the published literature. The cooling rates there are between 100 K per second and 1,000 K per second or so. If you do Nanuq without cold gas removal, you get about, and the fastest plunge speeds, you get up around 10,000 Kelvin per second. And with cold gas removal, you get up to 50,000 Kelvin per second. And this is for using thermocouples that have roughly 50 micron beads on them. So if you have smaller samples, 20 micron crystals, microcrystals, they can cool even faster than this. This 50,000 Kelvin per second, incidentally, is not that different than what's achieved in cryo-EM plunge coolers using liquid propane or ethane. But here we're just using liquid nitrogen. So it's really, really fantastically optimized cooling using liquid nitrogen. So we get huge cooling rates. That means that the cooling times below the protein solvent glass transition temperature, where the protein stops evolving its structure, can be less than 2 milliseconds, which means you can kinetically capture the room temperature structure and ligand binding conformation more accurately. You can also cool at intermediate and slow rates to simulate gas stream cooling, and for quasi-equilibrium cooling, which might give better diffraction outcomes in some cases, as we've already discussed. And the cooling is highly reproducible. The only real variable is the size of the crystalline surrounding solvent, which you have control over. And so this gives you an opportunity to do science-based optimization of your cooling and diffraction. With these large cooling rates, you can minimize cryoprotectant concentrations. In fact, you can eliminate them. You can eliminate all penetrating cryoprotectants. You should never have to use those to prevent ice formation. And this shows, here's a loop. It's got a solution with not enough cryoprotectant in it that has been hand plunged. And you can see it's clouded up saying it's got ice. You take the same solution, plunge it with Nanuq, and it comes out clear, which tells you it's fully vitrified. So we did experiments like that with a wide variety of different cryoprotectants. And what you can see here is that using Nanuq, so this is not protein crystals, this is just water plus cryoprotectant. This is the worst case scenario. Protein crystals require less cryoprotectant in general than do these solutions. But in this worst case scenario, you can see that the Nanuq allows concentrations of cryoprotectant to be reduced by a factor of typically 3 to 4 to very low values that should have little perturbing effects. Here's an example from a user at U of Florida. They had crystals that they were soaking in 20% sucrose and then hand plunging, and they kept getting ice. And then they just got rid of the sucrose and plunged directly using Nanuq and got rid of the ice and got the diffraction they needed for their experiment. So you can use less or no cryoprotectant. As I said, you don't need penetrating cryoprotectants, which is great if you're doing ligand binding studies. You don't need to do cryosoaks. All you need to do is do something to help to either cryoprotect or remove residual solvent on the surface of the crystal, which you can do using quick swipes through a dilute cryo solution or oil. Because cryo concentrations are always small and you don't spend much time in the cryoprotectant, you don't get crystal damage from it and you don't get your crystals dissolved by it. And as I've said, it's really great for ligand and fragment screening because you're going to have nice, clean internal density in your solvent cavities. No cryoprotectants in there. And so it'll be easier to recognize if you've got weak binding, for example. So what are some key advantages of Nanuq? You cool immediately after harvesting with complete confidence. You get no ice from cooling, from ice floating in your liquid nitrogen, or from frosting while you're loading your crystals into the puck. You don't have lost crystals due to manual plunging and loading accidents. One of our Nanuq customers at a major pharma company said that they go to the synchrotron every 2 weeks, or they send samples there every 2 weeks. They typically have 2 or 3 loops show up that had no crystals on them, and another 2 to 5 samples that were ice balls. Since getting Nanuq, and since they've been using it for the last 10 months, they haven't seen a single lost crystal or a single snowball, and they freeze all of the samples they send to the synchrotron using Nanuq. You can easily sequence and track your samples in pucks to optimize your data collection. And if you've got a big lab where you have people who have their own favorite weird techniques, or fresh graduate students and experienced postdocs, you can get everyone in your lab using the same reliable protocols. So overall, the instrument provides the reproducibility and flexibility you need to rationally optimize your cooling protocols. So how can you get the technology? Well, you can buy it. We'll package it up and ship it to you and install it at your site. And we can help you write instrumentation proposals. We can provide justification statements, whatever you need in order to secure the funding to acquire one of these. It may not be easy. The timeline for obtaining the required funding for some academic users may be long, and we want to make sure that everyone can have access to this technology. So we have a user facility here at Mitogen's home in Ithaca, New York, that you can use to cool your crystals and see the improvements that Nanuq can deliver. So how do you get your crystals here? Well, you can, if you live near enough to Ithaca, you can drive with them by car, or you can ship them to us. You can come in advance to our facility and set up plates, and we can monitor them for you. You can send just solutions in plates, and we can set them up for you and monitor them. And then when it comes time to cool your crystals, you can do it yourself with our support, or you can have our expert staff harvest and cool them, and then ship them in pucks to your favorite synchrotron source. We have a wide variety of equipment available at our site, more or less everything that you'll need to grow your crystals, harvest them, cryoprotect them, cool them, store them, ship them. So you won't need much except for your protein and crystallization solutions. If you want to give this a try, go to our website and go to the Nanuq Access Facility page and fill out the request trial form, and we'll then get in touch with you and to get the information we need from you to move the trial forward. So we're really hoping that a lot of you will take advantage of this, of the access facility, to see how much of a difference using a Nanuq can make to your workflows. So thank you very much, and we'll be happy to take your questions now.
Thanks, Rob. So thank you everyone for all the questions that you've sent in and for all of the attention that you've given to the webinar. So Rob, the first question, what size crystals would have the largest impact for the fast cooling?
So generally, what matters is the total thermal mass at the end of your mount. And so it's the crystal size plus the amount of surrounding liquid. Biggest impact will be below 100 microns and below. And of course, as you go to smaller and smaller crystals, the cooling rate goes up and up and up. That said, no matter what size crystal you have, remember it's not just ultra fast cooling. Nanuq really gives you complete control of the cooling process. It makes cooling rate a variable that you can use like hydration or cryoprotectant concentration to optimize the diffraction quality of your crystals. And so if you have a big crystal, you can cool it really slowly. You can cool it at an intermediate speed and see what happens. But in terms of this, the ultra fast cooling without penetrating cryoprotectants and getting full kinetic, getting as much kinetic capture of room temperature conformation as possible, sort of 100 microns and below is where you're going to see the biggest effects. But even at 300 microns, you're going to see benefits of the cold gas layer removal and the fast plunges on cooling rates.
Great. Another question. Do you believe it would be possible for the variable rate cooling to trap molecules in various conformations?
Yeah, absolutely. So you could cool very slowly. It depends. You can use this as a science tool as well. You could, if you have crystals of a certain size, let's say you have 50 micron crystals, you soak them in something that triggers a conformation change or a reaction that proceeds fairly slowly at room temperature, and then you can use different cooling rates to trap different populations. Okay, so if you trigger something that happens in a fraction of a second after triggering it, that's not gonna, the variable cooling rates probably aren't gonna help. But there are lots of reactions that proceed more slowly, lots of conformational changes that proceed more slowly, especially in the constrained environment of a crystal. And by using variable cooling rates, you should be able to trap different populations.
Great. The next question. What non-penetrating cryoprotectant would we recommend?
So in our work, I'm a big fan of oils. Just swiping crystals through oils until you get all the liquid off. That seems to work really well. I think other than that, you can use a penetrating cryoprotectant like glycerol if it's a quick swipe, right? So it takes a finite time. Depends how big your crystals are. If they're tiny, there's no such thing as a quick swipe. The glycerol will go right in. But for bigger crystals, you could even use glycerol. But large molecular weight pegs are probably safe. I think other people are more expert at that than I am. I might look at Jim Flogreth's review article. He probably has some suggestions there.
Do we recommend still removing all of the excess solvent from around the crystals, such as touching off on a cover slip?
Um, so I think that's the optimal thing to do in practice. If you have thin needles or plates, you don't want you want to maximize throughput, and unless you've got highly skilled people, they can destroy a lot of crystals trying to get all the solvent off. So I think you do the best you can, and just make sure that whatever residual solvent, try to have as little as possible, and cryoprotectant, add cryoprotectant, a non-penetrating cryoprotectant to it as needed.
Great. Question on how are the pucks loaded into the system?
So there's a tool that just it's like a set of tongs that you grab the puck with the tongs, and there's a lid. You open the lid on the Nanuq and just drop it in, and they just drop onto one of the 4 platforms that captures the puck, and then yeah, and I think those platforms are indexed so that there's a well-defined, they know what the particular orientation of the puck is.
Great. There is another question on it. We mentioned unipucks. Could Nanuq be adapted to be used with other types of pucks?
Yeah, I mean, I'm sure, yes, I think that would be pretty straightforward. You should let us know what you had in mind. There's quite a bit of clearance inside that liquid nitrogen dewar that holds the pucks. So I think they could adapt. They could accept other designs. Yes.
Yes. So the carousel gears do have puck adapters designed to work with both the ALS pucks and the spine baskets. And should there be another puck format out there that we're unaware of, certainly interested to hear what people had in mind. Another question is, and this may be referring to the watershed system, are we able to mount directly onto a home generator, or is transferring via the pucks the option?
Yeah, that's a good question. I mean, it's designed to, the instrument's designed to load them into the pucks. Keep everything isolated until you've frozen all your samples so that you don't get any frosting, and also load them into the pucks because, get them into something where it's going to be as easy as possible to remove them without damaging them or without allowing frosting. So we put everything in the pucks, and so you would have to remove the puck, and then transfer to your home source.
Great, and so the last question that we got a few times here that we'll address live, will the slides be made available? And the answer is yes. So we plan to make both this recording of the entire webinar and the slide deck available to all of the registered attendees, whether you're able to stay for the whole presentation or not. So in the next day or two, we'll be sending out an email that includes a link to the recording, as well as a PDF copy of all of the slides that we presented today. And so with that, I would like to say thank you to everyone who attended and listened. We appreciate it. We'll be happy to answer any questions that you have offline if they weren't addressed live, and happy to answer any questions that come up in the next day or two. We'll also plan to be sending this follow-up email and hope to contact individuals to discuss interest.
Yeah, we're also very interested in possible interesting science applications of this technology. I think one of the questions on trapping conformational distributions touched on that, and I think there's a lot of possibilities here and opportunities for collaboration that we'd be interested in hearing about.
Right, and that's directly in line with the Mitogen mindset, is that we want to enable interesting science and develop technologies that allow researchers to do great things. So thanks again. Thank you, Rob. And thank everyone for listening, and we look forward to connecting with you to discuss Nanuq further.